The focus of this lesson is on solving rational inequalities using test points. The first step is to make sure one side of your inequality is 0. So if it is not, you need to add or subtract the term to move it over so that it is. And in this case, we'll need to subtract 1 from both sides in order for that right-hand side to be 0. So if I do that, I'm left with x minus 12 over x subtract 1 is greater than 0. Now I am dealing with rational expressions in this problem, so it would be helpful if each of these rational expressions had a common denominator. And we could see that the common denominator for all these terms, if we look at them, their denominators are 1 and x, so the common denominator would be x. So I need to rewrite each of these expressions with an x in the denominator. And so when I do that, we can see in this first expression we'd have to multiply the 1 by x to get x, so we'll have to do the same thing to the numerator. So x times x is x to the second. In the second expression we already had x, so we keep what we had in the numerator, which was a negative 12, so minus 12. And then in the third expression we multiply by x, we do the same thing up top, so we get x over x. So minus x over x is greater than 0. And then what that allows us to do is rewrite that as one rational expression. I'm going to put it in order. So it's x squared minus x minus 12 all over x is greater than 0, which then I could factor the numerator, which would be x minus 4 x plus 3, and the reason being negative 4 times 3 multiplies together to give me negative 12, but adds together to give me negative 1. And then what I need to do is I need to determine the boundary points. Now the difference between rational inequalities versus polynomial inequalities is the boundary points come from both the numerator and denominator of your rational expression. So where your numerator is set equal to 0 and where your denominator is set equal to 0. So I'm going to go ahead and take my factors of my numerator, which are x minus 4 and x plus 3, and I'm going to set each of those equal to 0. And then I'm going to do the same with the denominator. So my factor of the denominator is x, and where it's 0, I'll just set it equal to 0. And so if I solve each of these, this one gives me x is 4, x plus 3, I could subtract 3 from both sides, I'll get x is negative 3. And then this one's already solved for, so I'll just rewrite it, but x is 0. So these three values are my boundary points, which you can see I have them here. And I can go ahead and draw this on a number line. Now the difference with rational inequalities versus polynomial inequalities is some of your boundary points may be zeros and others may not be. So when you think of a rational expression, you are 0 when your numerator is 0. So possible zeros, this is a 0, x is 4, and x is negative 3 is a 0. X is 0 came from the denominator, so that's actually where you're undefined, so not where you're 0. So when we're solving our inequality, we need to keep that in mind. So wherever you're undefined, you're going to always have kind of an open circle at, because you're never going to have a solution there. Whereas at negative 3 and 4, which are zeros, those may be included depending on what our inequality says. Now our inequality says where we're greater than 0, so we're not including the zeros. So those also will be, in a sense, open circles because we're not including zeros. So we are not going to include any of our boundary points in our solutions, hence why when I write my intervals, they all have parentheses. So you can see that there are 4 intervals here, from negative infinity to negative 3, from negative 3 to 0, from 0 to 4, and from 4 to infinity. So then what I would do is I would pick a test point within each interval. So anything to the left of negative 3 would be maybe negative 4. Between negative 3 and 0, you could pick like negative 2. Between 0 and 4, maybe pick 1. And then 4 to infinity, you could pick 5. And again, what we're concerned about is what is our overall sign when we plug those values into our factorization form of our inequality. And so if I plug in negative 4, so I'm going to use this table up here to kind of demonstrate this, then up in the top in the numerator we get negative 4 minus 4. That's going to be negative. And then negative 4 plus 3 would be negative, divided by, if you plug in negative 4 for this x, you'll get a negative. So overall, that ends up being a positive divided by a negative, which is overall negative. Do the same thing with your test point for negative 2. Negative 2 minus 4 would give us a negative value. Negative 2 plus 3 will give us a positive value. And then if I plug in negative 2 for x in the denominator, that'll give us a negative value. So this ends up being a negative divided by a negative, but that's overall positive in sign. If I do the test point of 1, 1 minus 4 is negative. 1 plus 3 is positive. And then if I plug in 1 in that denominator, that's also positive. So I end up getting a negative divided by a positive, but that's negative overall. And last, I put in 5. 5 minus 4 is positive. 5 plus 3 is positive. And then I'm dividing by 5 would be positive. So positive divided by a positive is in fact positive. And so in our inequality, we're looking for where we're greater than 0. So where we're positive, basically, is what that's saying. And so the inequalities in which we were positive were from negative 3 to 0 and from 4 to infinity. And so we write our solution as negative 3 to 0. Again, we don't include those endpoints because we are not concerned where we're 0, and we don't include undefines. And then the same thing for 4 to infinity. We don't need to include the zeros because we're not concerned with where we're equal to 0. And so our solution at the end of the day for our inequality is negative 3 to 0 union 4 to infinity.